Hello, my name is Sam Epstein, and this is my talk on the Independence Postulate. The Independence Postulate is a finitary Church-Turing thesis and was introduced by Dr. Levin in 1984. It douses Gödel's hopes of finding new axioms of mathematics through physical, non-algorithmic means. The Independence Postulate implies that outliers exist in the physical world, say fluctuations in weather conditions. It implies Occam's razor is a preferred method in induction. Physically realizable games that have good randomized players will have simple winning deterministic players. IP implies bounds on binary classifiers. And as shown in the previous video, IP presents complications for the many worlds theory. The bibliography can be found on the slides of my website. The statement is as follows. Let alpha be a sequence defined by an n-bit mathematical statement, and the sequence beta can be found in the physical world with a k-bit instruction set. Then the mutual information of alpha and beta is less than k plus n plus c for some small absolute constant c. This statement involves Kolmogorov information and is applied to the following three definitions depending on the context. K is the prefix-free Kolmogorov complexity. M is the algorithmic probability. So you have mutual information of finite strings, mutual information of a finite string with a halting sequence, and mutual information of infinite sequences. From Levin, we get the following statement. Thus, a physical sequence of all mathematical publications has little information about the mathematical sequence of all true statements of arithmetic. This is of little concern because the latter has, in turn, little information about the stock market. The independence postulate can be seen as a finitary Church-Turing thesis. The problem with the Church-Turing thesis is that it says nothing about finite sequences. For example, singletons languages containing large preferences Hn of the halting sequence is trivially computable. However, by the independence postulate, n is less than the shortest non-recursive definition of h of n, dubbed nr, summed with the shortest physical address of hn, dubbed ADDR. We see that the halting sequence is mathematical, so the shortest non-recursive definition of Hn is just a description of n, which is O of log n. Thus, the shortest address of h of n is greater than n, and thus h of n is forbidden. IP implies the definition of so-called recursive finite sequence. A recursive sequence has an algorithmic description nearly as short as their higher level math description. By IP, only recursive sequences exist in reality. As shown, the shortest address of a sequence X is greater than the difference of the shortest algorithmic description of X and the shortest non-recursive description of X. Mathematical strings have non-recursive definitions much less than their length. A mathematical sequence must be algorithmic to be physically attainable. That is, the sequence must be algorithmically compressible to small Kolmogorov complexity. For example, 9999 to the millionth power is mathematical, algorithmic, and physically obtainable. IP is an unproven statement supported by provable theorems, which are the deterministic and probabilistic conservation inequalities. Theorem 1 states that a function f cannot increase information about a target sequence y. Thus, interrogating an oblivious witness cannot glean any information about the crime. Theorem 2 is a probabilistic conservation inequality. A probability can only increase information about a target sequence with exponentially decreasing measure. A more detailed discussion about probabilistic conservation inequalities can be seen at the end of my first video. IP is not restricted to producing the exact target sequence. As stated in 1113, IP is much more comprehensive. Church-Turing prohibits only generating the target sequence itself. IP bars all strings with any significant information about it. So IP can be applied where CT cannot. Thus, the Church-Turing thesis states you cannot generate the halting sequence. This is in contrast to IP that states all sequences with high information about the halting sequence have high address. Thus, we will use this property for the remaining applications of IP. It is well known there is no consistent completion of penal arithmetic based on a recursively enumerable set of axioms. However, Gödel had his doubts, thinking there could exist a mechanical, non-algorithmic means that could produce new axioms in mathematics. However, in 1113, these hopes were dashed. In 1113, it was proven that every consistent completion of penal arithmetic has infinite mutual information with a halting sequence. Thus, by IP, no such completions can be found in the physical world. This is why H was referred to as Turing's password in 1113. One common goal in computer science is to find the hidden part of the environment. This task has been called inductive inference, extrapolation, passive learning, etc. The complete environment is a huge string X. Known observations restricted to a set that X is a member of. This set is D. For example, in thermodynamics, X can be seen as a record of every particle's position and velocity. An observation of some macro parameters, such as pressure and temperature, restrict the possible observations to a set D of hypotheses consistent with the observation. One method used to select hypotheses is to leverage a priori distributions P and select the environment with the largest prior. For enumerable distributions, i.e. generatable as outputs of randomized algorithms, there is the universal prior, the algorithmic probability M. This semi-measure has the following well-known properties, and there is no lower computable refutation to the statement X is generatable by M. Thus, when the universal prior is used, inductive inference becomes an exercise of Occam's razor. However, there exists a potential complication. There could exist a collection of hypotheses G representing a concept that could have a combined a priori measure greater than that of the simplest element X. Or making the endeavor more murkier, it could be that G is just a set of all complicated hypotheses with greater a priori measure than X. However, the EL theorem states that this is only a mathematical construction. All the universal prior of a set with low information with the halting sequence will be concentrated on its simplest element X. Thus, by IP, the only physically realizable observations will have a concentration of measure on X. So Occam's razor is the preferred strategy. In the cybernetic agent model, a player P and an environment Q exchange actions, or natural numbers. At some point, Q can declare that P has won, otherwise the game continues indefinitely. An example game is if Q has a K-set formula and P has n variable assignments, all starting at false. At each round, Q tells P the clauses that are not satisfied. P can choose up to K variables and sends them to Q. If all the clauses are satisfied, then P wins. In fact, there exists a useful theorem that can be applied to this example, called game de-randomization. It states if there's a probabilistic player that wins with good probability, then there is a simple winning deterministic player. As always, there is a mutual information term with a halting sequence. Through a little reworking and applying Moser and Tardis's algorithmic Lovász local lemma, you get the following bounds on a winning player to the K-set game. Thus, by IP, all physical realizable environments with randomized players has deterministic players. Classification is the task of learning a binary function from strings to bits. The learner is given a sample consisting of pairs of a string and a bit and outputs a binary classifier that should match the target function as much as possible. Occam's razor says that the simplest explanation is usually the best one. Simple hypotheses are resistant against overfitting to the sample data. With certain probabilistic assumptions, learning algorithms that produce hypotheses with low homomorph complexity are likely to correctly predict the target function. The following theorem shows that the samples can be compressed to their count plus an information term. Thus, by IP, all physically realizable samples can be compressed to their count. For the remainder of the talk, we will discuss outliers. There is no agreed upon definition of an outlier, but here are three reasonable characterizations. First, an observation that deviates so much from the other observations as to arouse suspicion that it was generated by a different mechanism. Second, a person or thing or fact that is very different from other people, things, or facts, so it cannot be used to draw general conclusions. Third, an observation whose value lies outside the set of values considered likely according to some hypothesis, usually one based on other observations, and an isolated point. So it looks like outliers are mistakes or errors of some process, but as we will show, outliers are an intrinsic part of such processes. In algorithmic information theory, anomalies or outliers are modeled using deficiency of randomness in both finite and infinite cases. The definitions are as follows. The deficiency of randomness is equal up to an additive constant to the log of the universal lower computable p-test over natural numbers or infinite sequences. A sampling method A is a randomized method that maps n to n unique strings. As the size of the output of A increases, there is a good chance that a member of the output contains an outlying state, that is, has high deficiency of randomness. The term P in the deficiency term is a computable probability over natural numbers. The term C is an additive constant dependent on the probability and sampling method. A continuous sampling method takes an integer n and outputs n unique infinite sequences. And there is a corresponding continuous sampling method theorem with slight differences in the constants. The term P is a computable probability measure over infinite sequences. The term C is a constant dependent on the probability and the sampling method. Outliers exist in the outputs of probabilistic algorithms. More specifically, if probabilistic algorithms whose outputs are non-atomic measures over infinite sequences, outliers are guaranteed to be present. The following theorem gives a lower bound on the measure of outlier states. The additive constant is solely dependent on the universal Turing machine. This theorem was reworked and applied to the case of computable metric spaces to be discussed later. In addition to being emergent in sampling and probabilistic methods, outliers are emergent in dynamics. In this slide, we'll present a theorem showing that outliers are emergent in the dynamics of ergodic transformations over the Cantor space. Let T be an ergodic and measure-preserving function over the probability space of the Cantor space, its Borel sets, and the measure lambda. As the number of iterations of T increases, it is guaranteed to hit outlier states. The greater the outlier, the lesser the bound. There is also a theorem for non-ergodic transition functions over the Cantor space, but it is out of the scope for this talk. Outliers occur in the dynamics in computable metric spaces. Such spaces contain a dense countable set of ideal points, and the distance between these points is computable. A computable probability over X is a constructive point in the space of all Borel probability measures over X. A uniform test takes in as input a probability U and outputs a lower computable U test. The function T is a universal uniform test and used as an outlier score with respect to U. Dynamics are modeled using a one-dimensional transformation group. Thus, this function is continuous with respect to T and the input of G. The theorem states for starting states that are not exotic, the Lebesgue measure of points with large outlier scores has the following lower bound. So we've talked about anomalies emergent from algorithms and dynamics. However, many systems are too complex to be algorithmic. Take, for example, your local weather forecast. This picture shows a big anomaly. Such systems are not computable, but they do have an address. We model observations as infinite sequences of infinite sequences. Of course, in the real world, infinite sequences of observations do not exist, but infinite sequences model processes that are potentially never ending. The result is as follows. The term T is a score of how likely outliers appear in the prefixes of gamma. If T is low, then the outliers appear quickly in the sequence gamma. If T is large, then outliers appear slowly. If the outlier score is bounded, then T is infinite. The theorem states that T lower bounds the amount of mutual information gamma has with the halting sequence. Then you can use IP to show that observations gamma with large T scores do not exist in the physical world. Thus, all sequences gamma of observations have outlier states that appear at a certain rate. Put another way, it's hard to find observations with small anomalies and impossible to find observations with no anomalies. This concludes my talk. Thank you for listening.